Hello, this is Greg Ristein from Olympus. I'd like to welcome everyone today to this webinar on inspecting composite wind turbine blades with advanced ultrasonic phased array technology. This webinar will address the challenges of inspecting materials such as fiberglass and carbon reinforced plastics that are used to construct wind turbine blades. Since the industry has been searching for simple and reliable solutions for some time, this webinar will highlight a variety of tools and techniques from Olympus that make it easier to detect and size flaws in different areas of the blade. Our presenter today is Andre Lamar. Andre is a business development manager with Olympus Scientific Solutions Americas, specializing in the aerospace and power generation industries. He's a graduate in engineering physics and holds a master's degree in materials science. He's accumulated more than 20 years of experience in phased array ultrasonics. This informational webinar should last about a half an hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Andre. Andre, take it away.
Thank you, Greg. Good morning, everybody. Welcome to this webinar about the use of ultrasonic phased array for the inspection of composite wind turbine blades. So, without further, let's go. The content of the presentation is like this. We'll first describe what is a wind turbine blade, and of course, a few words about how ultrasonic phased array inspection works. Then we'll review the detection capabilities of ultrasonic phased array, as well as the productivity of ultrasonic phased array, and then we'll go to the conclusion. Okay, so let's look at the wind turbine first. So there's four main components that we can easily identify in a wind turbine. First is the wind turbine blade that we all know. The wind turbine blade, in fact, generates aerodynamic torque from the wind. The nacelle here has all the electrical power, so it converts the torque into electrical power. The tower holds the nacelle and the rotor blades in the wind, and they also provide access to the nacelle itself. We also have the foundation that ensures that the turbine stays upright. It's interesting to note that all these components require NDT testing to help to ensure their integrity at different stages during manufacturing, construction, and maintenance. In this presentation, we will focus on the use of ultrasonic phased array for inspecting wind turbine blades during manufacturing. Okay, what is a wind turbine blade? Well, a turbine blade is composed of an outer shell, like this, that is reinforced by one or many internal structural beams that we also call spars. The number of spars depends on the size of the blade. Some might have only one, some might have three and more. The interior of the blade is hollow, and depending on the manufacturer, the spar could be rather an I-beam spar, like this one here, or a box spar, like this one. The I-beam spar, let's look at it for a little. The I-beam spar is composed of two spar caps and one shear web, while the box spar is composed of two spar caps and two shear webs. In both cases, the spar caps are attached to the skin with adhesive. A few words about the material used in the construction of wind turbine blades. Some material like glass reinforced fiber, carbon reinforced fiber, some wood sometimes is used, adhesive, resins, honeycomb structures, and coating are the material that compose wind turbine blades. To make things more difficult, all these materials are not acoustically friendly, so it's a challenge to inspect this turbine blade with ultrasound. What type of flaw do we find into a wind blade? There's different types of flaws that we can find. We can see that we can have porosity here. We can have this bond between different structure of the blade itself. We can have delamination. We can also have inclusion of foreign material. And also wrinkles that are out of plane waviness can be found into wind blade. Also, during the inspection or the construction of the wind turbine blade, it's important to evaluate the adhesive itself. So what has to be evaluated here? We have to evaluate the thickness of the adhesive, the width of the adhesive, and if there is some area where there's lack of adhesive or bonding. Few words about principles of ultrasonic phased array. A phased array probe is composed of multiple piezoelectric elements. Typically, it can go from 16 elements up to 128 elements. And we use a group of elements to create a beam, and then we multiplex the beam over the length of the array. Unfortunately, here we cannot have animations, but you have to understand that this beam here will move electronically in that direction. Another way to represent that would be like this. If you use a conventional UT probe, when you move the probe in one direction, you cover only one line. When you use a phased array probe like this, using the linear capability, when you physically move the probe in that direction, you cover this whole area here. So it results in a large coverage in one pass and keeping a fine resolution. This is this technique that we are going to use when we inspect wind turbine blade. The image that we will obtain are typical image obtained with ultrasonic phased array system, which is the C scan here, which is a mapping of the area that is inspected, like if we look at it from the top. The B scan, which is the view from the side of the wind turbine blade or the cross section, or the D scan, which is the view on the other direction. And of course, the A scan, which is the raw information coming from the probe that we process to obtain all these different images. Olympus offers different type of instrument for wind turbine blade inspection. There's the Omniscan A6, which is a portable instrument that can drive only one phased array probe. Is used for manual inspection, rather for prove-up or on the blade itself during maintenance. The Omniscan MX2 can also be used in a manual mode, but also in a semi-automated inspection as well as fully automated. So this system can drive multiple probes and can be hooked with a scanner like this that is manual or a motorized scanner like this one. And then for high productivity, Olympus offers the Focus PX, which is a PC-based instrument that can drive multiple phased array probes. This instrument also is scalable. That means that it can drive hundreds and hundreds of elements, resulting in a very high productivity with good resolution all the time. Okay, the key of the inspection of wind turbine blade is the probe. So Olympus has developed a low-frequency linear phased array probe. This probe can have frequency of 0.5 MHz and also 1 MHz. It is composed of 64 elements. The length is 96 mm, a little less than 4 inches. The elevation is 22 mm, close to 1 inch, and the pitch, that is the resolution of the probe, is only 1.5 mm or 60 mils. And as the probe is quite large, we also use plastic housing to reduce the weight of the probe, to make its use more easy. If we look at the frequency spectrum of the probe, look at this is the signal A scan and the FFT obtained with a 1 MHz probe using the Omniscan MX2. So let's look at it for a minute. We can see here that the signal is pretty damp for a 1 MHz probe. When we do the FFT, we see that the center frequency is 1 MHz, the bandwidth is 80%, the lower frequency at -6 dB is 0.6, while the upper frequency is 1.4. Means that the probe works into 0.6 to 1.4 MHz with damp signal. Now, if we look at the 0.5 MHz phased array probe with the Omniscan MX2, again, we can see that the signal is damped very well here. We see 1 cycle and 2 cycles. So that's a very damp signal. The center frequency is 0.6 MHz, while the bandwidth is 100%, which is excellent for a low-frequency probe like this one. But please pay attention to this. The lower frequency at -6 dB is 0.3 MHz, while the upper frequency is 0.9. So that means that even if the Untitled Chapter 2 has a cutoff frequency of 0.6 MHz, as you can find in the spec, it can also drive successfully a probe within its whole spectrum range from 0.2 to 0.9 MHz. So a probe like this, using the Untitled Chapter 2, the Untitled Chapter 6, as well as the focus peaks, can be used for this kind of inspection without any loss. So this is a very important conclusion here. So that opens, in fact, the Omniscan to low frequency application as casting, honeycomb structures, and difficult to inspect material with 0.5 MHz phase array probe. So please, I would like everybody to pay attention to that conclusion. Okay, now we have the probe, but we also have to mount the probe. So we need some holders. So we develop different type of wedge and probe holders here. So we have one of them that is semi-contact probe holder for deep penetration. It means that between the probe and the part, there's a very fine layer of water, which is about 1 millimeter or so. So of course there is some ringing from the interface here when we inspect, but this configuration is used to inspect very deep in the material with high power. When we need near surface resolution, we would use aqualine delay line, as this is the equivalent of a water column, and we have very good coupling between this aqualine delay line and the part, resulting in a very good near surface resolution. So both holders are available in flat configuration or curved configuration to sit on the wind blade better. Now let's look at the result obtained with ultrasonic phase array for wind turbine blade inspection. We're going to focus here on the spark gap inspection. So if we look at the configuration we have here, we use an automated scanner. We use the Omniscan MX2 and the probe that we just discussed. And all the result here will be presented as an amplitude C-scan. Of course, this is an artistic view here. We do not project the C-scan on the blade, but it's just to give you an idea of what can be found. What can be found, excuse me, on the blade. Okay, let's look at the result. So here we see the scanner better. So if we look at the C-scan, first, this axis here is the length of the blade that we also call the span direction. This axis is the cross-section, also called the chord direction. We can see different area on the C-scan here that corresponds to different area of the cross-section of the blade. So those red area here correspond to this flange's position right there and right there. While we have blue and green colors, it corresponds to the bonded zones between the spark gap and the shell. And these are the ones that we're going to pay more attention today. So we can see here that the flange, when the signal gets through the blade, it reflects on the interior of the blade with very high signal, resulting on a red color on the C-scan. If we look at the bonded zone right here, the ultrasonic beam goes through the spar, travels through the adhesive, and then travels down to the shear web here, resulting on the no or very weak signal back to the blade. That's what explains the blue and the green color. We're going to see that in more detail. So what can we get from this information here? First, this dimension here gives us the width of the adhesive zone. We can also find some area where there's local deficiencies of the bonded area. And always remember that with the use of the low frequency phase array probe, the sizing resolution for such flaws is 1.5 millimeter or 60 mils. Now let's zoom on the bonding evaluation, on the bonding area. We can see in this example here that the bonded zone gets narrower and narrower as we move in that direction to a point where we have complete disbond. So in that example, with the cursors here, we can measure that there's a 80 millimeter long section that is totally disbond, and we also have the confirmation from the B-scan here, where we have a very strong reflection from here. Now, if we look at what seems to be the good bounded zone, if we zoom in this area here, we can also see that we have localized unbounded areas that are approximately 20 by 20 millimeters square. Adhesive thickness measurement can also be performed with ultrasonic. Depending on the adhesive material, the echo from the interface shell and the glue and the shear web can be detected. In that example here, we have two echoes. This first one here is coming from that position. The second one is coming from that position. So by measuring the distance or the time between those two echoes using the right velocity, we will obtain the thickness of the adhesive. The delamination can also be found quite easily. In fact, delamination are the most easiest flaws that we can find in wind blade because they are a good reflector for ultrasound. But sometimes, like here, the delamination is very close to the back wall, so it might be difficult to find them with a C-scan of amplitude. So the use of a C-scan of time of flight here will really highlight the position and the size of the delaminations, like we can see here. Wrinkles. As mentioned earlier, wrinkles are out-of-plane alignment of layers. They are very important to detect during manufacturing because they reduce the blade tensile strength, and they can create out-of-plane delamination. The technique, the ultrasonic technique used here is not really a reflection technique. It's more a, it's not a reflection technique, it's a resonance technique that is used. So what does that mean? It means that the layers will resonate at a certain frequency, so that's why the frequency of the probe is very important, creating in that case a reflection of flat reflection of layers right there. But you can notice at that position that this will deviate from the horizontal plane here. So how do we evaluate the wrinkle? We measure the vertical deviation here and also the length of the wrinkle. So those two information are important to define the characteristic of the wrinkle so that the engineering can make their calculations to see if a repair is necessary or not. Productivity of ultrasonic phased array. So we come back to the earlier example. Right, we use a automated scanner. We can see in that example that the scanner is 5 meters long and the scanner width is 0.5 meter. In that example, the scanning direction means that the probe will move in that direction, so at the length of the blade, and the indexing will be in the cross-section like this. So we don't have movie, unfortunately, on this webinar, but the probe will move like this, index, come back, index, come back. So the indexing is about 4 inches, and the acquisition resolution remains all the time 1.5 millimeter in both axes. So the speed that we can achieve the inspection here is 2 meters square in 40 seconds, or 3 meters square per minute. So this is very fast inspection, and we also always record the C-scan and the A-scan. Note here that the scanner is not an Olympus product. The other way to do the inspection is this one, and this is the one that we prefer, is to have the probe now to move in the correct direction and index in the length of the blade like this. So the probe will go like this, scan, index, scan, index, and so on, resulting again in a very fast inspection, keeping the resolution of 1.5 millimeter in both axes. And the operator can follow live the C-scan of the spark cap here. So during the inspection, the operator is able to follow the evolution of the inspection and find flaws. In conclusion, ultrasonic phased array can be used to inspect wind blade with low frequency probe of 0.5 and 1 MHz. The flaws, such as wrinkles, delamination, and these bonds can be detected and characterized. The adhesive thickness and its width also can be evaluated. The 1.5 millimeter resolution enables small flaws to be detected and accurately sized. The linear scan capability enables fast inspection while maintaining 100% coverage of the part. Off-the-shelf phaser unit can be used as a standalone or integrated with automated scanner. And also, the use of ultrasonic phaser can also be considered in the maintenance program of wind turbine blades. Well, thank you.
Well, thank you, Andre. On behalf of Olympus, I'd like to thank the attendees for joining and Andre for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event, whether you attended or not, will receive a follow-up email with links to the archived presentation for further viewing. I'm going to turn this back over to Andre once more for any Q&A that he may want to address. So, Andre?
Yeah, sure. Thank you, Greg. Well, we have a question from Marc-Antoine Blanchet. Thank you for your question, Marc. The question is, could you please clarify the distinction between the spar caps and the shear web? Yes, absolutely. So allow me to come back to one of the first slides. Okay, so if we look at that image here, okay, on the I-beam, the spar caps is this area here that is, let's say, linked to the shell of the wind blade, while the shear cap, or the shear web, excuse me, is this section of the blade that link the two spar caps together, right there. So in that case here, there's only one shear web. In that case, there's two shear web, okay? So this is the difference between those two components. There's other questions. Can you review the F50 versus omniscan frequency setting again for the lower frequency probe? Are you saying that the frequency setting doesn't clip the signal? I'm not sure, Rob, that I understand your question, but let's go back to the F50. First, I guess you are probably a user of the omniscan. Am I correct, Rob, if I say that? Okay. Yes, very good. So, Rob, you must know that we always Olympus always characterize the omniscan to have a cutoff frequency at 0.6 megahertz. But it's important to understand that the cutoff frequency is -3 dB. But there's still a lot of energy under 0.6 megahertz, and this is what we experimented here by using the 1.5 megahertz. So there's two effects here when we use a low frequency probe. First, as you know, the omniscan is limited to 500 nanoseconds. So if we use half period, we should use a pulse width of 1,000 nanoseconds. But by using 500 nanoseconds, we lose just a few dBs compared to 1,000 nanoseconds. But it keeps the frequency of the probe intact, so it doesn't have any effect on the frequency spectrum of the probe. But the electronic itself has a curve, has a drop under 0.3 dB, and its result is about 0.4 or 0.5 dB of loss under 0.6 megahertz. So overall, we have a loss over, let's say, around 7 to 9 dB, which is, we believe, acceptable for the use of a 0.5 megahertz probe. Now, so Rob, does it answer your question? Okay, I'll wait if Rob can answer, if it answers this question properly. We have a lot of questions. Thank you everybody for your question. Okay, there's too many now.
Andre, which
turbine blades manufacturer? Of course, we do not mention, we're not allowed to mention the people that we are working on. I mean, it's a question of respect for our customers. That we cannot, publicly mention who we are working with. Yes, Greg, sorry.
Oh, no, I was just going to say that if you wanted to address these questions personally, by email afterwards. That's another option.
Yes. Okay.
If we're running out of time.
I think, are we fine with time? So if
we are fine with time, I
think I can still answer a few questions.
Yeah.
Let's see the question. Oh, one interesting question from Jay Amos. They are all interesting, by the way. But Jay, I got a question about the resonance used for wrinkle detection. Well, what I would suggest is that you look at the work done by or Dr. Robert Smith from the University of Bristol. Dr. Smith has published many articles and publications that you can find on the web that explain in very more detail the resonance method used to characterize wrinkles. So I would rather give you this reference so that you can look at. Kumaran has a question. Can you go to the image of bonding of spar cap to shear web? The adhesive thickness measurement, did we get the echo of shear web as well as spar cap? Then how do we determine the bonding width? Well, there's two things here. Let's look at the image. Okay, so how to determine the bond? The echo we have here is, as you mentioned, it comes from the first echo here comes from the interface between the spar cap and the adhesive, and the second one from the adhesive and the shear web. So this position here will measure the thickness of the web of the adhesive. But to measure the width of the adhesive, which will be in fact this position here, we have to look at the C-scan. So if we go from this position to this position, we will measure the width of the adhesive. So I hope I answered your question. Marc-Antoine is asking, have you ever tested the low-frequency probe through 50 mm of material for circumferential crack at the blade roots? No, we haven't, but we would be very interested to test it if we have any samples that we can make a test on. All right, so I think I went through most of the question. So Greg?
Okay, Andre, thank you again.
Yes.
And thank you to all the attendees once again for your participation. Thank you for your interest and taking the time to attend this event. We will see you again next time. Stay tuned to our website for more webinar information. We will be having more throughout the year, and we hope to see you with us. Thanks again, and that'll do it for today.
Thank you, Greg.